Hi everyone, Aaron here. Direct observations of chemical or phase reactions are the fundamental data type used to calibrate thermodynamic models. In the Enki project, we use the phase reaction database file in order to capture this type of information. And specifically, the data having to do with the reaction is stored in the reaction tab, RxN. This video provides a detailed overview of the reaction tab for phase reaction datasets, enabling you to accurately digitize phase reaction experiments. Just like the experimental conditions tab, the reaction tab starts with a couple of columns identifying which particular experimental run is represented by each row. Additionally, there is a reaction studied column. To fill out this column, you must provide a balanced chemical reaction representing the reaction that was studied in that particular run. In this case, for Holdaway 1971, they were studying andalusite goes to kyanite, and therefore they used the official phase symbols for both andalusite and kyanite separated by an equal sign. For a more complex reaction, we need to look to another example. Chernovsky 1976 looked at a set of complex reactions involving anthophyllite. One particular reaction was this reaction between talc and forsterite going to 5 enstatites plus water. Notice that the stoichiometric coefficient 5 precedes the symbol for enstatite, and there is no space between them. In some cases, you may have multiple reactions which occur simultaneously in a given run, in which case you need to include all of the formulas for the reactions present, for the reactions occurring, and separate them by semicolons and spaces. After the reaction study column, we have a number of columns having to do with the presence of flux, which can greatly affect the kinetics of the reaction. The first column is flux type. Here you can see that you can select water, which is a very common one, or other common flux types, including oxalic acid or molten salt, as well as an amount of flux, which can either be a qualitative value like trace or excess, or a numerical value, in which case you can simply enter the value and choose your units as per usual. The contact geometry is also a very important part of analyzing these phase reaction data sets. As depicted in this diagram, there are 3 typical experimental geometries used during these phase reaction experiments. The simplest is planar contact, where all of the reactants shown in blue and all of the products shown in red are on separate sides of the container or experimental chamber. They can either be single crystals or they can be fine grains. The only thing that matters is that they are fully separated from one another. The most common type of setup is the mixed grain setup, in which both products and reactants are ground into fine powders and mixed together. This can either be in the case where you have a roughly equal proportions of products and reactants, or they can also represent seeding experiments where the chamber is filled primarily with reactant and only a small amount of product is mixed in to act as seeds for the reaction. The other typical setup is the single crystal setup, in which a large crystal of the reactant or the product is surrounded by a powder of the product or reactant. All 3 of these are possibilities of typical contact geometries and must be indicated in the data file, as they strongly affect the kinetics of the reaction. Also important to the kinetics are an indication of the grain size. Ideally, the grain size would be directly reported in the paper, although this is quite rare. So, in order to handle this problem, we provide multiple ways of giving an indication of the grain size. The first is simply a grind duration. How long did they grind their materials before running the experiment? Otherwise, the grain size can be reported directly if known, in which case it can be reported in microns or millimeters. In this case, they did not report direct grain sizes, but rather the mesh number of the sieve used in preparing the experiment, and thus we also provide mesh number as one of the options for grain size. In cases where the single crystal measurement is used, the size of the single crystal should be reported as in terms of mass, using either grams or micrograms. There are many different methods used to assess whether the reaction has proceeded toward the reactant side or the product side of the equation. One typical method is weight difference when using single crystals. This is where a single crystal is surrounded by a powder and it is measured before and after, and the difference is used to indicate which direction the reaction is proceeding. This can be indicated with the weight diff method, and the reaction metric unit should then be a unit of weight, like micrograms. In this case, the reaction metric 0, value, and error columns can be filled out in accordance with the values reported in the paper. The 0, in this case, represented no change from its initial state. The reaction metric value column stores the difference in the weight of the single crystal after versus before the reaction took place. And the reaction metric error column stores the analytical error on that measurement. Based on the sign of the reaction metric value column, we can therefore assess what the results of the reaction are. Another typical method is the optical method, in which they use the petrographic microscope to simply observe the textures or the sizes of the grains to determine whether grains were growing or shrinking, and therefore inferring the reaction direction. In this case, because this is a qualitative metric, there is no data appearing in any of the reaction metric columns. Finally, you need to report the results and, if relevant, the reaction direction certainty. The results column is reported using a specific format. It is given as a list of phase symbols, for instance, AND for andalusite, followed by a symbol indicating the direction of the reaction. This can be either a plus, a minus, or an equal sign, indicating that that phase increased, decreased, or was found unchanged during the reaction. Additionally, each of those symbols can be followed by a question mark indicating uncertainty. The overall certainty on the reaction direction is also often reported in papers, and thus you can provide an indication of the reaction direction certainty in its appropriate column. For that column, you can report either definite, probable, unresolved. Unresolved would be equivalent to no change observed, or biased. Biased is a special result that is reserved for cases where the authors have identified some reason why the reaction boundary is not to be trusted from that particular experiment. In this case, bias is reported for any of the samples which contained fibrous sillimanite or fibrillite, since it is known to strongly bias the reaction boundary by hundreds of degrees Celsius. Anytime you use the biased flag, you should describe in the notes column why you believe that particular run to be biased. For completeness, we should also take a look at a more complicated data set involving multiple phases. Again, let's take a look at the Chernovsky 1976 data set. Because that data set focused on reactions involving many phases, you can see that the results column involves a list separated by semicolons and spaces as usual, indicating which phases were seen to increase, decrease, or see no change over the course of the reaction. That's all for now. Thank you very much.